Have you ever stopped to think about what happens when you upload a photo to the cloud? I mean, where does it actually go? Well, today we're going to pull back the curtain on the incredible system design behind cloud storage services, like Amazon S3. We're going to unravel the architecture that makes it all work.
Just to give you a sense of the scale we're dealing with, let's just start with a number. It's estimated that Amazon S3 alone stores over 500 trillion objects. Seriously, that's not gigabytes or terabytes, that's 500 trillion individual photos, videos, and documents. It's a number that's almost impossible to wrap your head around.
And that brings us right back to the big question, doesn't it? How on earth is it possible to store, organize, and then instantly pull up any one of those trillions of files without ever losing a single byte of data? It's not magic, I promise you. It's just one of the most brilliant feats of software engineering out there. So to build a system that can handle that kind of scale, we first have to understand why the tools we use every day just aren't going to cut it. Look, storing a few files is easy, but storing billions or trillions of them? That requires a completely different way of thinking. This is what we call the billion file problem. Okay, so why can't we just use a normal database for all this? Well, trying to use a traditional database for this is kind of like trying to send a sofa through a mail slot. It's just not what it's built for. These databases, they choke on blobs or large files because they're optimized for tiny, structured records that change all the time. Like the balance in your bank account. If you try to stuff a huge photo in there, it's just incredibly inefficient. It slows the whole system down to a crawl. Object storage, on the other hand, is custom built for these big, static files. So what exactly is an object? It's actually a really beautiful and simple concept. Just think of it like a self-contained package that has three key parts. First, you've got the data itself, the actual bytes of your photo or video. Second, you have metadata, which is just data about the data, things like the file name, when it was created, stuff like that. And third, a globally unique ID. And here's the crucial part. Objects are immutable. That means you can't just edit a little piece of it. If you want to change it, you have to replace the whole thing with a new version. All right, so we know we need a special kind of system. Let's try to build one from the ground up, starting with just a single machine. How do we make one server as reliable as humanly possible? So, a simple way to get more space is just to add more hard drives, right? You could split your file, put half of it on disk 1 and half on disk 2. This doubles your storage and can even make reading the file faster. But, and this is a huge but, you've also just doubled your chance of losing everything. If either one of those disks fails, poof, your entire file is just gone forever.
To solve that, we need redundancy. The first approach is called mirroring. It's super straightforward. You just make an exact copy of everything. It's very safe, but it also means you need to buy twice as many disks for the same amount of storage. The second and much more efficient method is parity. Now, parity is a little bit like magic. It uses a really clever mathematical trick. Think of it like solving a simple equation. If you have 2 plus x equals 5, you can instantly figure out that x has to be 3. Parity works in a similar way, letting the system calculate and rebuild the missing data from a failed disk by using the data that's still there. No full duplicate copy needed. Pretty smart, huh?
Now, a single server, no matter how awesome and reliable we make it, can't hold trillions of files. It's just not possible. The only way you can ever achieve that kind of scale is to distribute all that data across thousands and thousands of servers. So, how do we make that jump? Think about it. How does the system know which one of the thousands of servers is holding your specific photo? This is where a technique called sharding comes in, and it's powered by something called a hash function. You can think of a hash function as a perfect sorting hat for your data. It takes the unique name of your file, runs it through this mathematical function, and it deterministically points to exactly one server in the entire cluster. And it does this every single time without fail.
And the key here, as this slide points out, is random distribution. A good hash function acts like a perfect card dealer, spreading the files out totally evenly across all the servers. This is so important because it means not only is the storage load balanced, but the traffic, all the reads and writes, is also spread out. No single server ever gets overwhelmed.
Okay, so we've protected ourselves against a single disk failing. But what happens if an entire server just catches fire? Or what if a whole data center loses power? To be truly reliable, the system has to be designed for large-scale disaster. So here's the crucial step. We take that same principle of redundancy we used for disks, and we just apply it at a much bigger scale, across entire servers, and even across different geographical locations. Your data isn't just sitting on one machine,
It's replicated and distributed across multiple machines in multiple data centers. So if one server goes down, the system just seamlessly redirects you to a replica without you ever even noticing anything happened.
And this incredible level of redundancy leads to this almost mythical number, 11 nines of durability. This is the gold standard for high-end object storage. What does that actually mean? It means that if you store, say, 10 million files, you can expect to lose a single one of them only once every 10,000 years. For all practical purposes, your data is permanent.
So let's put all the pieces together. From a single disk failing all the way up to a whole data center outage, we've built up the resilience of our system piece by piece. So what does the high-level blueprint for a massive cloud storage system actually look like?
When you upload a photo, it's basically a three-step dance. First, your computer talks to the API service. You could think of that as the bouncer at the front door. It handles your request. Then, the metadata service acts as the system's librarian. It doesn't hold the file itself, but it knows exactly which shelf to find it on, using that hash function we talked about earlier. And finally, the data service is the massive warehouse itself, the thousands of servers that actually store your file's data, all replicated and kept safe.
But wait, there's more. It doesn't stop there. Layers of really smart features make the whole system truly robust. Checksums act like a digital fingerprint to make sure your data doesn't get corrupted. Versioning is basically your undo button, protecting you from accidentally deleting something important. Multi-part uploads are for those giant files, letting you upload them in smaller chunks so a drop connection doesn't mean you have to start all over again. And garbage collection is the system's janitor, constantly tidying up and reclaiming space. Every single one of these is another brick in this incredibly resilient wall.
From hosting a simple website to powering these massive data lakes for artificial intelligence, this incredible architecture has become a fundamental building block of the modern internet. So really, the question isn't just about how it works, but now that you know the design, what amazing things can you build on top of it?